see here. Okay. So I want to start off with something that we know how to do from these previous solving equations that we did. So before we look at 3 to the x equals 1 over 81, let me put this to the side so that we can just kind of compare it with something that we know how to do. Let's say I gave you e to the x equals 1 over 81. Now, we want to solve for x. Look at the location of x, right? X is setting up as an exponent. So what did we do before to solve for x, or to allow for that x to be in a better location?
Take the log.
Take the log. Well, we took the natural log of both sides, right? Yesterday, 2 days ago, or the day before. So, but yeah, we're gonna take the log of both sides because we want to take advantage of these log properties. And then once we have something that is in this form, we can bring that exponent down, and that x will be in a much better location for us to solve for it. So we'll take the natural log of both sides. Now, as a reminder, natural log is just a shorthand way of writing log base e. Okay, so these are the same thing. We've been using ln because it's just been less, just having to write less every time, right? Prefer to write this, right? But I want to kind of go back to this log base e, just so that I can kind of go through some demonstrations and also see some similarities between what we're going to be about to do. So essentially, I'm taking natural log of both sides, but I'm going to just call it log base e. So I'm going to take log base e of both sides, which is the same thing as natural log. But look at how things pair up nicely here. So same thing as saying natural log of e to the x. We can bring that x down in front, right? So our expansion properties is not limited to just natural log. It applies to all logs. So bring that x down in front, right? We're just applying this property here. Right? Exponent can freely come down in front. Now we said that natural log of e is equal to 1, right? And the reason why is because natural log of e is log base e, and because the base and the value matches, that's what allows this to go away so nicely. So we know that goes to 1. So I have x by itself. X is log base e of 1 over 81, or we've been saying natural log, right? So I'm going to bring it back to natural log. Okay, so the reason why I suddenly changed to this form of log base e is it's going to help us connect with the form we're going to see with example 1. But we know how to do this, right? Review. So now, what if we approach it from this perspective, where the base is still an exponential function, but the base is not e, the base is now 3. We're still going to take the log of both sides so that we can get that exponent to come down. But I want to purposely match my base so that I can get that 3 to hopefully go away nicely. So now instead of taking log base e, I'm going to take log base what?
3.
Log base 3, yeah. I'm trying to get that. I want to strategically choose a base that will clean up nicely. So I'll take the log base 3 of both sides. So in much the same way how log base e of e goes away, we can expect log base 3 of 3 to go away. But first, this is I can use my exponent property. I can bring that x down in front. Log base 3 of 3, just like log base e of e, just like natural log of e. We'll just, essentially what we're doing is we're pairing an exponential function with its inverse, right? They're going to undo each other, just like how natural log and e are going to cancel each other out. So we're left with log base 3 of 1 over 81. Now we can go actually a little further here. What's can I represent 81 in terms of 3? Maybe as an exponent. 3 to the 4th, right? 3 to the 3rd is 27. 3 to the 4th is 81. So what if I make this 1 over 3 to the 4th? And stealing some of the space below here, but 1 over 3 to the 4th is same thing as 3 to the negative 4, right? So I can rewrite this 1 over 81 all the way to this form of 3 to the negative 4, and that is a nice form to have because it matches our base. We can bring the negative 4 down in front. We know what happens with log base 3 of 3. So the answer is just negative 4. Cleans up nicely. So just like how we use natural log to get rid of base e, we can use log base a to get rid of any base that we're dealing with. But the same concept applies. We take the log of both sides because we want the exponent to come down, because we want to take advantage of those expansion properties. Now, if you look at number 2 here, we have log base 2 of x equals negative 4. Let me go to a problem that we recognize how to do. Let's say I had natural log of x equals negative 4. If I want to solve for x, x is stuck inside the natural log. I want to find a way to get rid of the natural log. We're going to involve its inverse, because we know inverse and its function are going to undo each other. So what can we do to both sides? Yeah, let e be the base, right? Now, natural log is same thing as log base e. I just want to kind of show this log base e of x equals e to the negative 4. And the reason why e to the natural log goes away nicely is because my bases match, right? This is log base e. This is also e. They're going to go away nicely. And I'm just left with x equals e to the negative 4. And I can clean that up to just make it 1 over e to the 4th. Okay, so we know how to do this, right? So if I want to get rid of natural log, I use its inverse, which is exponential function e to the x. Now here, I also want to solve for x, but x is stuck inside a log base 2. So how do you think we can get rid of log base 2? Yeah, set 2 as the base, right? We know the inverse function of log base 2 is just 2 to the x. So if I can pair a function with its inverse, that's a quick way for me to remove or to reduce and simplify. So just like how e to the log base e goes away, I can get log 2 to the log base 2 to go away. So that leaves me with just x equals 2 to the negative 4, and that reduces to be 1 over 2 to the 4th, which is 1 over 16. Okay, so I just want to connect with something that we already know how to do and just make some slight adjustments to account for the different bases. Okay, any questions there? So in a similar way, when we talk about derivatives of bases other than e, there's also going to be a connection with the rules that we already know how to use. So let me start with something that we know that we recognize. We should recognize natural log of u, right? The derivative of natural log of u is just a nice clean u prime over u. Sorry, there's no equal there. So d over dx, derivative of natural log of u is just u prime over u, right? We know that. But what if it's not base e? What if it's not natural log? If it's base other than e, we call it a because they all have a similar pattern. So a could be base 2, could be base 3, could be base 10. Oh, and then as a reminder, we have natural log to represent log base e, and then we have log to represent log base 10. So because base 10 and base e are used so often, we have kind of a shorthand form of writing them. So that's just as a side note. Okay, so back to our derivative here. What I want to show you is that our derivative is going to be very similar to what we have. There's also going to be a u prime over u. It's still a log expression. We still have u prime over u, but it's not base e. And what the rule is going to do is we're going to have to do a little bit of a conversion into base e, and then we have a nice u prime over u. So we have to account for the fact that it's not base e. We convert it into base e, and the way we do that is we include a coefficient of 1 over natural log of a. That is a bit of a change of base, converts it into base e, and then once it's in base e form, our derivative is going to look just like how we did with natural log of u, just u prime over u. Okay, so let me do a quick example, and then we can look at some that are a little bit more involved. Let's say I have y is equal to log base 7 of 3x minus 7x squared. Okay, not natural log, not base e, but it is a log expression, and it looks like it's going to match up nicely with this rule, right? So let's just see what the rule says and follow that. Okay, what's my a value? 7. So the first part is a conversion into base e. So 1 over natural log of 7. So that takes care of the fact that it's not base e. It does its conversion into base e. And now the rule looks just like how you would do with natural log. U prime over u. Yes?
On the worksheet, it says u prime over u prime.
Sorry, yeah, that's wrong. It should be u prime over u. Typo there. Okay, what's u prime?
3 minus 14x.
Mm-hmm. All over my u value. Okay, questions there? So example 3 and 4 and other examples that we're going to see, we're going to expand first, if we can, before we do our derivative rule. So natural log of AB can be expanded to natural log of A plus natural log of B. Same thing, log base 3 or log base 5, log base 6 of AB is equal to log of that base of A plus log of that base of B. So all these properties still stand for non-base E logs. So I just want to kind of remind us of that. So if we look at example 3, it's not base E, but we can still look for expansion things that we can do so that our derivative is easier. So is there anything that we can do here to rewrite the problem?
Put 1/3 at the front.
Yeah, let's come. Anytime I see a radical, I'm thinking, how can I make that a little bit visually more helpful? So I'm going to rewrite that as raised to the 1/3. Okay, I know this is not natural log, but do you see any properties that that we can apply?
Exponent.
Yeah. So just like natural log, log base 5 also has access to that property, right? We can bring that 1/3 down. So no derivative yet. All we're doing is we're just moving that exponent so that we don't have to deal with a messy u value. So everything is nicely cleaned up. We have our rule. So we move to our derivative. Okay, what comes down first?
130.
Yeah, coefficient, right? Coefficient for any derivative just kind of tags along, right? It doesn't go anywhere. We just have to make sure we include it. Times.
1 over ln 5.
Yeah, we have to do a little bit of conversion, right? It's not base E, so we got to do a little bit of conversion in front. After we get past that, then it looks just like your natural log rule, u prime over u. I'm going to just attempt to just get this all under one fraction, but you don't have to. Okay, questions with 3. Okay, look at number 4. That's a messy parentheses there. What can we do to avoid a messy derivative rule?
Product. Or,
Product, yep. What's the other one?
Or, yeah, quotient.
Quotient property, right? And then once you get past quotient property, maybe there is an exponent property you can take care of as well. Okay, so see if you can expand that, and then you can approach it with this rule. Now there's a hidden base here. What's that hidden base? 10. Okay, so it's good to include that because it's going to come up later in our derivative. So see how far you guys can get. Let me check your progress. basically it's this thing, just replace your column with this thing. Okay, so expansion first, right? So just like how we can do natural log of a over b into natural log of a minus natural log of b, if I have log of a over b, I can expand it into log of a minus log of b. And we have some more additional expansion properties available. We can bring this exponent down in front. And now this is ready for our derivative rule. But why do we not bring down this 3?
It's not, yeah.
Yeah, it doesn't see the 5, right? It's not, I mean, we could bring that 3 down if we separate it into log of 5 plus log of x cubed, but it's just not worth the effort. Because your u value is already pretty easy, right? The derivative is not going to be an issue here. But the reason why we want to expand here, because we don't want our u value being this whole mess, right? We want to bring that 3 down so that we have a nice, much easier u value to work with. So now we have a relatively easy problems. We have 2 of them. Both of them are, we're going to apply our new rule that we just learned, log base a of u. We can leave it in this form. I just decided I wanted to do a little bit of cleanup with my last step. Okay, any questions here? So let's look at exponential function that is not base e on the next page. So let me start by reviewing what we do know how to do. We know how to handle derivative of exponential function that's base e. So as a reminder, we know that e to the u is just an easy process, right? It's just the original function times the exponent's derivative. Right, we know that. We know e to the u. Now, what if it's an exponential function that's not base e? What if it's base 2 or base 3? What if it's 3 to the x or 5 to the x? They all kind of fall under the category of base a because they all kind of, we have to basically convert all of them into base e for all these other bases. So just like how the previous log problem, we have to do a little bit of conversion with that natural log of a, same thing here, okay? We're basically converting it into base e, and then the process will look the same as before. It'll be the original problem times the exponent's derivative. So there's conversion that has to happen in the base e. So instead of in the denominator, now it's in the numerator. So natural log of a times, now it looks just like your original rule. Original function times exponent's derivative. Original function times exponent's derivative. Just a different base. Questions there? Okay, let's look at example 5 to kind of practice that rule. This is 5 raised to the x squared minus 2x. This is not base e, but it's still an exponential function. So we can say y prime is equal to, let's match the rule, natural log of what? What's my base? 5, yep, natural log of 5.
Yeah, 5x.
times the original function times the exponent's derivative, which is what? So I want to just make sure that you guys see how similar it is, right? We just have to do a little bit of adjustment because it's not base E, but once you get past that point, it looks a lot like how we handled e to the u. There's not a lot of cleanup that we can do. This 5 is stuck inside natural log. We can't combine it with this 2. This 5 is connected to that x squared minus 2x. We can't multiply that 5 with anything either, so these kind of have to stay separate. Okay, example 6. We have y is equal to x times 4 to the negative x. Okay, so 4 to the negative x, we recognize that as an exponential function that is not base E, so we definitely have to use that. But there's something else that we have to involve here. Product rule, right? X and 4 to the negative x, they're obviously different terms. We can't combine them. They're being multiplied together. So because of that multiplication, if we want to find the derivative, got to involve product rule. So let me set that up and see if you guys can finish the problem. We want to talk about how we can maybe clean that up a little bit, find common denominators, but show them. Your steps look pretty good, so let me just go through that. F prime, x becomes 1, g function stays, f stays. When we get to g prime, natural log of a times the original problem times the exponent's derivative. And then I see an opportunity here. Both of them have 4 to the negative x. If I push that down to the denominator, I get a quick match with common denominators, and I just decided to put it as one fraction. Okay, Paul, do you see what you need to see? Oh, sorry. That was a while ago. I didn't realize I missed that message. Okay, any questions here? All right, so there's particle motion here as well. I think I want to save this for tomorrow. I want to just spend the rest of the class today. Let's practice a bit more with these rules. get more comfortable with them. So this is on the other handout, which is, or the other printout, which is the base A derivatives and 5.5 classwork page. But if you don't have it, it's okay. I'm just going to show you the problems that I want us to do. So we're going to find the derivative of each of these terms, these problems here. So these 5 problems highlighted. But all these look fairly complex, so we prefer not to jump into the derivative process just yet. What should we do with these log problems here? Expand first, right? So use the properties that's available to you. Product, quotient, power property. Now, I do want to point something out here. If you look at 55 and 56, there are multiple parts, right? So I want to kind of talk about how, how we can quickly expand when there's multiple parts in your expression. So let me just go over something like this. If I have log of AD over BC, I can expand that into log of A plus log of D minus log of B minus log of C. So basically, the idea is that any portion that's in the numerator is going to be part of a positive log expression. Anything in the denominator is going to end up being part of a negative natural log expression. So So expand as much as you can, and then once you've got them all expanded, your derivative should be fairly manageable. You shouldn't have to deal with a messy rules. You may have multiple derivatives to deal with, but they all should be pretty straightforward. And we're practicing these rules here. Right? Most of them are going to be this one. When we get to 40, though, that's an exponential function, so you'll use this. Okay, so try that. Let me see how you guys do. So try all the highlighted problems there. Expand first. So this minus log of that. And also, when you do derivative rule, make sure what shows up is going to be a natural log in your derivative.
Could you put the other equations in my computer?
Oh, yeah. Yeah, I'll put it on the board, yeah. This one, these ones you're talking about? Okay. And obviously you're going to adjust it with the log instead of the natural log. Guys, I only wrote down the property for natural log, but if it's logs of other bases, you need to adjust. So you got to make it logs of AB equals log of A plus log of B. Right? So when you expand, you got to keep whatever base the problem has. And only in the derivative is natural log going to show up. So in your expansion step, we shouldn't see any natural logs yet.
So your original scope, like I would leave that 2 as the base initially, and then you get the derivative. The answer is correct, but from this middle step, leave that 2 as the base. Do this separate these first, do prime, they can do that one down once this is separated. Okay, so you can extend a little bit more, there's another product not doing.
So it's X.
There we go. Yeah. So that's your A, and that your B, you X, that's log of X. So I separate this out.
Yeah, this one here, yeah. If I have 2 terms multiplied inside a log expression, I can further expand it out. Yeah, anytime you're looking at a problem and you're saying to yourself, this is a difficult derivative process, that probably means you didn't expand far enough. Okay, so if we're inside a natural log or log expression, our derivatives should be fairly manageable. I mean, assuming that it's not part of a larger product or quotient rule, but if it's just a log problem, we should be able to work our way down to very manageable derivative rules. Okay, all right, let me go through each problem with you. Looks like your steps, looks like you're doing pretty well from what I can see. All right, 53, expand, right? I see expansion properties. Now, I only wrote the properties for natural log, but you have to adjust for whatever base you're dealing with. So in this case, we're dealing with base 2, so you got to keep it in base 2. Log base 2 of the numerator minus log base 2 of x minus 1. Now you have two separate problems that you can take the derivative individually. So 1 over ln of a times u prime over u. 1 over ln of a, u prime over u. Leave it in that or continue fading out, up to you. Okay. Questions with 53. Okay, look at 52. We want to resolve that radical a bit, so rewrite it as a rational exponent raised to the 1/3. Keep going, right? We have a exponential power property. We can still keep going, so bring that 1/3 down in front. Now we have a much easier u value to work with. So our derivative, keep the 1/3, convert that to base e, so 1 over natural log of 2, and then the rest looks just like your natural log rule, u prime over u. Okay, questions? I'm doing these out of order, sorry. So here's 56 first. I see three terms. I see the 4, I see the x squared, I see the root 1 minus x, so I want them all to be separate log terms. And then within the second and third term, my denominators, they're both going to be negative because they're in the denominator. And then within the denominator, or within each of my second and third term, I see some additional expansion things I can do, right? I can bring those exponents down in front. Now I should have easier time with each of these derivatives. Now, what do you notice about log base 5 of 4? What is that?
0.
That's just a number, right? So a number's derivative is always going to be 0. So that's just going to go away. Okay. Coefficient, convert it to natural log, u prime over u. Here's 55. Okay, again, expand as much as I can. I have 3 parts that I'm looking at. The numerator, I can think of it as product property. Denominator is quotient property. Continue expanding. Once you expand out further enough, far enough that you can deal with that 1/2. We don't want to deal with this 1/2 too soon. Once it's separated from the other log terms, we can then bring that 1/2 down. And then we just follow the rules. Last one, number 40. Everything is set up and ready for the derivative rule, so we jump directly into our derivative rule. Natural log of a times a to the u times u prime. All right, any questions? Okay, good. I'm glad we got some practice problems in. So tomorrow, I want to do 3 things. We're going to do curve sketching. We'll do a little bit of particle motion, and then we'll do a little bit of review from 5.1 to 5.3. Inverse of derivative at a point. So I'm going to put the worksheets up under tomorrow's links, and you guys can hopefully print those out or have access to them. I am making progress with your tests. I'm about 85% of the way done, so hopefully I can get the rest of it finished, enter them into Infinite Campus. Hopefully I can return them back to you tomorrow. Okay. All right, if you're on Teams, have a great day. See you guys tomorrow.
Thank you, Mr. Yang.
Have a nice day, Mr. Yang.
You too, have a good day.